Hey guys, welcome back to a new video. In this short session, I will show a trick you can use when doing integration. It will allow you to immediately determine whether an integral is zero without doing any integration at all, and thereby save you a lot of calculation work. In short, the theorem states that any integral of an odd function over a symmetric interval is always zero. In what follows, I will briefly cover what an odd function is and why this trick is true. Then we will go over some exercises step by step to practice identifying such an integral, so that you will be more able to spot them in your own integration problems. And let's first look at what an odd function actually is. And the definition is the following one. F of x, so the function that we're looking at, is odd if and only if it has the following property. F of minus x, which means replacing all of the x's in our function with minus x's, is equal to minus f of x, which means that it is our original function f of x, but just with a global minus sign in front of it. And if this sounds quite abstract to you, I completely understand. That is why we'll look at an example to take away any confusion. Let's say that our function f of x is equal to x to the power of 3 minus x. And we now want to determine whether this function is an odd function. And to do this, we will look at the following, f of minus x. So this means that for each x in our expression of our function, we replace by minus x, which gives us the following. So the first x that we had to raise to the power of 3 becomes a minus x. And then the second x simply becomes also a minus x. Rewriting this, we see that if we raise a negative number to the power of 3, or any odd power for that matter, the minus sign can be put outside of these brackets. So we get minus x to the power of 3. And here we see that these two minus signs combine to become a plus sign. So we get plus x. Here we see that we can simply put one minus sign outside of these two terms and we get x to the power of 3 minus x. And what we see here is that we simply have this x to the power of 3 minus x, which is simply f of x. And of course, this minus sign should not be forgotten. So we have that this is equal to minus f of x. And what we have found now is that f of minus x is equal to minus f of x, exactly the definition that we had for an odd function. And therefore we conclude that f of x, which is in this case x to the power of 3 minus x, is indeed an odd function. Before we go to the exercises, let's first look at why the theorem that we're looking at is true, so that the integral of an odd function over a symmetric interval, so for example minus alpha to plus alpha, will always be zero. And to do this, we'll look at it from a graphical point of view, which will make it much easier to remember this trick. So we have the x-axis here, and we have the f of x, or the y-axis here. And as a function, we're again going to consider this function that we looked at before, x to the power of 3 minus x, of which we know is an odd function. And if you look up the graph of this function, then you will see that it will look something similar to this one. Now, of course, this is a rough sketch, but what is immediately clear is the symmetry that this graph shows. Namely, it has a point symmetry around the origin. And this will be crucial for our integration trick. In particular, we see the definition of an odd function into practice here. Because if we look at this point, for example, point x, then we see that its function value f of x will be right here. If we now look at the same point on the minus sign, so minus x and x being the same number, so this could be 3 and minus 3, for example, and we look at the function value of this point in minus x, then we will see that it will be minus f of x. And this is exactly what the definition of an odd function entails. We saw that f of minus x, so the function value of minus x, is equal to minus f of x, the function value in the positive x. And of course, from this graph, it becomes immediately clear why our trick is true. Let's say, for example, that we now integrate our function from -3 to +3, and we integrate x to the power of 3 minus x. Then we see the following. Let's say that indeed that this x is equal to 3. So x is equal to 3 and minus x is equal to -3. What does an integral mean? It means that we are calculating the area under the curve between these two bounds. Well, let's see what the area under the curve is. From -3, we integrate and we see that we're calculating this area right here. However, we cross the 0 point, and once we have crossed, we see that we're integrating this positive area right here. And we know from integration that areas beneath the x-axis are counted negatively, and areas above the x-axis are counted positively. So we see that this area is calculated with a minus sign in front, and this area is calculated with a plus sign in front. And because these two areas here are equal in absolute value, and we have a minus sign on one side and a plus sign on the other side, adding them up will always give 0. And this will always be the case for an odd function if we integrate over a symmetric interval from a minus some number to plus some number. And this is why this trick will always be true. And with this intuitive understanding, let's go to the exercises. The first exercise is to calculate the integral from -1 to 1 of the function x dx. We see that we are indeed integrating over a symmetric integral from -1 to +1. And therefore we have to determine whether f of x is equal to x is an odd function. And this is very easily done, because if we fill in f of minus x, meaning replacing all of the x's with minus x, we get minus x. And this is of course minus f of x. So we are dealing with an odd function. And this can also easily be seen if we look at the graph of f of x is equal to x. If this is the x-axis and this is the f of x-axis, then f of x will always be a straight line right through the origin. So if we now integrate from -1 to +1, then we see that we indeed again have this negative area right here and this positive area right here, which cancel each other out. So this integral will always be 0. Let's go to the next exercise, where we have to calculate a similar integral from -1 to +1, but now from the absolute value of x dx. And again, we are integrating from -1 to +1, so a symmetric interval. So we have to determine whether the absolute value of x is an odd function. And this is of course quite easily seen, because if we replace x with minus x, then we see that this absolute values simply negates this minus sign, and we simply get the absolute value of x, which is of course f of x. And we see that we do not have a minus sign in front of it, so this will not be an odd function. And in particular, this will be an even function, but that's something for another video. So this integral will certainly not be equal to 0. What it is exactly then, you can calculate with your favorite integration method. Let's go to a more complicated exercise. So we have to integrate from -2 to +2 the following function: x times the square root of x squared minus 1 dx. And we see that we are integrating over a symmetric interval. So let's see whether this function is indeed an odd function. So what is f of minus x? Let's simply fill this in. This first x again becomes a minus x. And then we multiply with the square root of minus x squared minus 1. And let's see what this becomes. We simply have minus x times the square root of minus x squared simply becomes x squared, because a minus sign gets squared away. Minus 1, and we close the square root. And we see now that we have the same function as we had originally, however now with this minus sign in front of it. So this becomes minus f of x. And we see indeed that f of minus x is equal to minus f of x. So this function is indeed an odd function, and therefore this integral will always be 0. So we see that this actually saved us a lot of time by, instead of solving this complicated integral, we simply looked at whether it was an odd function, and we determined that this integral will simply be 0 without doing any integration work. So let's now go to the next example, where we're looking at goniometric integrals. And this trick will actually be mostly used for integrals of this type. Let's say that we have to integrate from minus pi to plus pi of the following function: x times the cosine of x dx. Now at face value, you could solve this integral by using partial integration. However, we see that we are integrating over a symmetric interval, which already sounds some alarm bells. So we simply first look at whether we're dealing with an odd function by setting x equal to minus x. And let's just see what this becomes. So we get minus x times the cosine of minus x. And because we know that the cosine of minus x is equal to the cosine of x, which is something you learn in goniometrics, we see that we again get the function that we had before, x times the cosine of x, but now with a minus sign in front of it. So again, we get minus f of x, which means that this function is again an odd function, which means that this integral will be 0. And this is actually a good exercise to practice your integration skills. You can simply calculate this integral, like I said, with partial integration, and see whether indeed you get the result 0. Let's go to the next exercise, exercise 5, where we integrate from 0 to pi over 2 of the sine of x dx. And from this we immediately know that the sine of x is actually an odd function, because we know that the sine of minus x is equal to minus the sine of x. It's one of these properties that you learn in your goniometric classes. So we could conclude that this integral is also 0. However, that would be a mistake, because we are not integrating over a symmetric interval. We're integrating from 0 to pi over 2. And this is one of the conditions that needs to be met in order for this integral to be 0. So in this case, we cannot conclude that this integral will be 0, even though we're integrating an odd function. We're simply not integrating this odd function over a symmetric interval. So it's always important to keep in mind these two conditions. So let's go to the next exercise, where we have to integrate from minus pi to pi. And the function that we're integrating is the cosine of x times the sine of x dx. And again, this function can be integrated by a number of ways. However, we see that we're integrating over a symmetric interval from minus pi to plus pi. So it might pay off to just see whether this function is indeed an odd function. So what is f of minus x? Well, we simply replace x with minus x. So we get the cosine of minus x times the sine of minus x. The cosine of minus x is simply the cosine of x, and the sine of minus x is simply minus the sine of x. This minus sign here can be brought in front, so we get minus the cosine of x times the sine of x, and we see that we indeed get our original function again, however now with a minus sign in front. So we get that this is minus f of x. So this function is indeed an odd function, meaning that we can use our trick and say that this integral is immediately 0 without doing any integration. And at this point we can actually see a pattern, because here we have the product of an odd function with an even function. And we saw that the result is an odd function again. And this is more generally true in a similar fashion that we use our rules to multiply negative and positive numbers. We know that two negative numbers multiplied will give a positive number, and two positive numbers multiplied will also give a positive number. We know that if we multiply a positive and a negative number, that we will get a negative number. And this is exactly the same with even and odd functions. Multiplying two odd functions will give an even function, and the same goes for multiplying two even functions, this will also get an even function. However, if you multiply an odd function with an even function, as we did here, for example, the result will be an odd function. So this is just another layer on top of our trick that you can use to calculate these integrals more quickly. So let's go to the next exercise, where we have to calculate the integral from an interval of minus pi over 3 to plus pi over 3 of the following function: the sine of x plus 2 times the cosine of 2x dx. This integral can be easily calculated, but we see that we're integrating over a symmetric interval, so let's see whether this function is an even or odd function. We have that f of minus x is equal to the sine of minus x plus 2 times the cosine of minus 2x, simply replacing the x's with minus x's. We see that here we have minus the sine of x, because the sine is an odd function, and we add to this 2 times the cosine of 2x, because the cosine of minus x or minus 2x is of course the cosine of plus 2x. And we see here that we don't quite get our original function, because we do get this minus sign here from the sine function, but we lose the minus sign for our cosine function. So this is definitely not equal to minus f of x, and therefore this is not an odd function, and we cannot say that this integral is necessarily 0. It could be 0, but we cannot determine that out of the gate. Let's now go to the two last exercises, which will be quite more complex. So let's say we integrate from minus 2 pi to plus 2 pi. And the function that we're integrated is quite a complex one. We have the square root of x squared plus 1 divided by x times the cosine of x plus the sine to the power of 3 of x dx. And this is actually a very complicated function, and I doubt that it could even be integrated by hand. However, we probably could get a result because we're integrating here over a symmetric interval, and therefore it might be worthwhile to look whether this function is an even or an odd function. So let's look at f of minus x. This is equal to the square root of minus x squared plus 1 in the numerator divided by minus x times the cosine of minus x plus the sine to the power of 3 of minus x. And let's see how we can rewrite this. In the numerator, we have the square root of x squared plus 1, because the square of minus x is simply the square of x. And we look at the denominator, we get minus x times the cosine of x, because this minus sign remains where it is, and cosine of minus x is cosine of x. And we add to this the following. The sine to the power of 3 of minus x is simply minus the sine of x to the power of 3, because the sine of minus x is simply minus the sine of x. This simply becomes the square root of x squared plus 1 in the numerator, and in the denominator we get minus x times the cosine of x minus sine to the power of 3x, because this minus sign inside of the brackets also gets raised to the power of 3, but a minus sign raised to an odd power still remains a minus sign. And we see here that we can now pull this minus sign and this minus sign outside of the denominator and put it in front of the whole fraction. So we get minus the square root of x squared plus 1 divided by x times the cosine of x plus sine to the power of 3 of x. And we see here that we indeed have our original function, which is basically this one, with a minus sign in front of it. So we indeed again get that this is equal to minus f of x. And this is exactly what we had for the definition of an odd function. So this function, as complicated as it is an odd function. And this means that this entire integral is certainly 0. So we know that this complicated looking integral is 0 without doing any integration at all. So with this, let's go to the very last exercise, which is again a very difficult exercise. We integrate from minus infinity to plus infinity. The function is sine of x divided by the cosine of x times the sine of x minus x times the square root of 1 minus the cosine of x. And this again is a very complicated and even daunting looking function. And I wouldn't even know where to begin integrating it if I was just to integrate it. However, we see that integrating from minus infinity to plus infinity is also a symmetric interval. So again, it might pay off to look at this function and see whether it is an even or an odd function. So let's fill in f of minus x. This simply becomes the sine of minus x divided by the cosine of minus x times the sine of minus x minus x times the square root of 1 minus the cosine of minus x. And this can be rewritten as follows. The sine of minus x is simply minus the sine of x. So the enumerator we already have down. The cosine of minus x is simply the cosine of x. And the sine of minus x again is minus the sine of x. So we have minus cosine of x times the sine of x. These two minus signs combine to become a plus sign. So plus x times the square root of 1 minus. And again, the cosine of minus x becomes the cosine of x. So we again have the cosine of x under the square root. Let's see what we can do here. This minus sign and this minus sign and this plus sign can all be swapped and put in front of the fraction. So we have minus the sine of x divided by the cosine of x times the sine of x minus x times 1 minus the cosine of x under the square root. And let's see what we have here now. This function indeed returns here exactly. However, now we have a minus sign in front of it. So we know that this is equal to minus f of x, which makes it a manifestly odd function. And because this is an odd function, we know that this integral will be 0. So we know now that if we integrate from all the way of minus infinity to plus infinity, that this very complicated function is simply equal to 0 without doing any integration at all. And this brings us to the end of this video. And I hope that this trick of integration will help you greatly in your integrating endeavors. If you liked the video, meaning if you learned something, give it a thumbs up. And if you want to get notified by future releases, consider subscribing. And with that, I thank you guys for watching, and I will see you guys in the next one. Bye.